Do, 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 do. So what are we doing today? Let's do let's do um all right. I was trying to get back into C after all these years. I've probably learned more about C than I have ever done in these last few weeks. I don't ever recall using that much of C before. It was all C++. I remember us using C for OpenGL and an old 3D engine called Ogre 3D. Do you remember that? Oh my god, that was so long ago. And it's still in development. Incredible. Is there... Oh, there's a showcase. Oh, Torchlight 1 and 2 was created with Ogre? Amazing. Da, 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 da. All right, so you're going to get to see how we turn on all the cores of the system via code today, which is pretty cool. pretty easy too. I'm just going to go into my make file and tweak the amount of cores that I give the emulator. So I'm going to give it 4 cores. Did you say power off? No. I said power on. We're going to wake the cores that have been placed in a sleeping state. So I'm going to first see if it reports on those cores that I've just given it. Let's kick the tires. We don't have scrolling in the terminal. That's another thing we might have to do. So yeah, logical processors per core 4. Cool. Oh, and I've left the timer running, but all it's doing is writing to the keyboard. Just kind of silly. Mr. Kernel, what are you spinning on? Huh. Did World of Warcraft just try to update as I'm streaming? Really? How silly. Ah, interesting, actually. Yeah, so what I've researched is Lamini, which is the bootloader that we use, hands us the count of CPUs. Like it's already inspected the ACPI and it's placed a CPU count in a response for us. And what's really important about the processor IDs are these LAPIC IDs, because that's what is unique to each processor. So in this struct that we get back from this request object, I believe there is a CPUs array, which there is. And then in here we've got, for each CPU that there is, there's a LAPIC ID. I'm not sure how that differs to its processor ID. But then the other really important thing is this goto address. So we can set this goto address to a function for that core to spin up and start executing. And we're going to kind of prove that the cores are all awakened by just keeping track of how many cores did wake up. So call this CPU awake, and all we'll do here, I don't know if I can do that as loose as that because it's not using a lock. But we'll see. So we'll create a loop to just spin over the CPU count there. And then we'll try and wake all the cores up. Does your OS allow me to load games via tape? Yes, it does actually. It doesn't care about the medium. That you're plugging in, you know. But that's a thing too. So we're going to set out the roadmap. And devices, storage devices is probably high up on the list. Like being able to read and write to a hard disk is pretty important. But what we could place higher than that is networking. So it would be really fun for it to just, doesn't need anything to load and save off a hard drive, but if we get it connecting to the network and having it communicate with the internet, which is a big step because you've got to understand DNS and TCP, on top of the Ethernet frames that you have to code. But yeah. Da, 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 da. ChatGPT is your tutor. So I'm going to spin there. And then see if we can hit this kprint. Put this above. Wake the cores up. Boop. And then I think we can do this. Huh. So kprintf this waking up. I wonder how, once you're in this thread, do you understand what your LAPIC ID is? Or your BSP? I'm wondering if we need to set something up in the registers before calling this. Or I am thinking the function that you use. Do 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 do. In the protocol, go to address, someone writes this field, causes the part CPU to jump to a written address on a 64 kilobyte or stack request size stack. Oh, a pointer to the SMP info structure of the CPU is passed in the RDI. Okay, so it's already handled for us. So with this structure, we know what the processor ID is and the LAPIC ID. You should tell the Twitter about your stream. I did, and you liked the tweet like a minute ago. Oh, I keep forgetting this, right? So there's a bunch of registers. I need a cheat sheet. There's a bunch of registers that automatically get assigned to the parameters of a function. And RDI is one of them. So in here, you can actually get the SMP info object, which comes directly from the register that Lamani sets. So we can print the processor information here. And this will be, I wonder how this will function, knowing that it's multi-core now. And got to think about what you do atomically or not. So let's write the LAPIC ID of the processor while waking up. And let me just check what the processor ID is. Maybe it shares the same processor ID as the others. Not sure that was like that. So waking up, report the LAPIC ID, report the processor ID, and then, oh, we'll increment that variable here. All right, let's see. I've got a feeling, though, that I may just have to halt those cores, or it'll cause a protection fault. I'm going to comment that out for now. I want to see what the behavior is. CPU count. A uint 64? Why on earth is that a uint 64? Hello? That's a huge number. Oh. Oops. Int. Yep. Let's get that guy the same type. No guts, no glory, indeed. Alright, it's going to be interesting. And I think we died. And I'm going to assume it's because we didn't halt the cause, maybe. Or it might be this. Right. So that definitely was what was happening. So if we look in here, CPU count is 4. Waking up, waking up, waking up. I got 3 of them. Oh. Is it because one of them's the Bootstrap ID? We can test for that. Let's try it. But yeah, we're not atomically writing to that terminal now, which is a bit funky. I could put a spin lock inside of here just to make the log look pretty, but should we do that? So we will lock it there and unlock it here, just so we get the terminal looking neat. Now, if that LAPIC ID is the same as our BSP, like we don't want to wake that one up, do we? Because it's already woken. We'll just do a lock on that because it's going to use and then we'll continue, but we'll also need to update the CPU's awake. Hello, Chili. Good to see you again, buddy. Okay, let's give that a whirl. Da, 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 da. I can't trust that terminal. BSP LAPIC ID is 0. The CPU count is 4. We're getting 3 wake-ups. We're getting LAPIC IDs 1, 2, and 3. I mean, I guess it makes sense, right? It's just not detecting if we have the BSP LAPIC ID. Let's Let's just write that into the log, just so I understand what it's firing. Wait, why aren't we getting that log? Let's just comment out this stuff. It's probably going to complain about unused functions now. No. Oh, there's an error. Multiple definitions of a lock. Oh. That could have been a problem that's been here then since the start, so oops. Let me not wake up the CPU then. Do the logging. All right. Yeah, so the first one is the Bootstrap processor. And I'm assuming that when you ask that one to wake up, it's not going to do anything. So if I ask it to wake up here, knowing that's the Bootstrap processor, I'm guessing it's not going to run. Let's just confirm that. Right, so it hasn't. So it's firing up 0, core is BSP, and then firing up the other 3 cores. So yeah, the BSP does not get fired up. So I guess what we can do is CPU's awake is 1. We'll start that at 1. CPU's awake, right? CPU's awake is less than count. All CPU cores are online. That was a test line, and then that's actually waking the core up. Don't want to do this stuff anymore. Don't need to register that. And okay, that should do it. CPU count 4, waking up, Lapic ID 1, processor ID 1, waking up, Lapic ID 2, processor ID 2, waking up, Lapic ID 3. So, why? Why didn't we get this line? Cores online. try and just print that. Cores on line 4. Okay, I wonder if it prints waiting. And it does. So we hit the while loop. Oh, I know what the problem is. You should always mark variables that are accessed via multiple threads as volatile, because the compiler is going to strip that while loop away because it doesn't feel like it's ever going to change. So now we've told it, hey, this is a volatile variable. Don't optimize my code. We should get what we want now. And we have. So we've got the whole kernel booting up now. So if we look in the log, there we go. So we've got waking up stuff here, waiting for CPUs, waking up, processor ID cores on line 2, cores on line 3, cores on line 4. All CPU cores are online. And then it carries on with the kernel. So we now have proper detection of the kernels coming online, the cores, which is great. Now, once you're in this thread, so once you're in this thread on a new core, you've got the context of your registers for that core. So at that point, you're probably going to want to do something like change the FS or the GS registers to point to this information. So you've got the LAPIC ID and the processor ID. And that's how you link up of knowing what thread, or rather what core context you're running on. So I wonder if that's how it's done though. Oh, I see. There's another parameter you can smuggle into the thread. It's the extra argument. It's an uint64, so we can put an address in there. Let's just have a look at the documents for that. I want to see what it says. A free for use field. So they've clearly made this for smuggling in something for you to point to help set up your CPU context. which is good. Because what, looking at the reference of another operating system, what they're doing is they're creating a custom structure that captures things for the processor. And then that's what gets smuggled in on the extra. I just bring it in here. It's what gets smuggled in. So the extra argument here is cast to this CPU local struct. And then they're doing a GDT and an IDT, which is what I was going to ask actually. So every core, because it's got its duplicated set of registers, you're going to have to load the GDT and the interrupt table for each core. And then this task state switching concept, this is what we need to look up. So we need to learn about what this TSS is. I believe it's about it's something to do with switching the state per CPU, but I'm not sure. And then what's this VMM switch to? Top level memory page map. And then this threading stuff. What's the threading stuff doing? Shed, maybe it's probably defined in. Who is defining that event, maybe? Huh. Might be in a header file. There you are. So that to me looks like everything to achieve running programs. Time slice, yield await, CPU context, CPU local. Which is the capture of the SMP stuff. What's the CPU context then? Oh, the registers. All of the registers. Interesting. So there's a lot of unpacking there for my domain knowledge. I'm not going to be able to go that far in at all. So that'll be Yeah, that's a deep understanding of like proper scheduling of application threads and processes. But we don't want to get that far, so we're going to come way back out of there. And we're going to grow this concept naturally and slowly. Right, so I'll build up what I want to do with these cores. Because at the moment, so let me just make some notes here. So load the GDT, load the IDT. What were the other core things it was doing? So idle thread, kernel process stuff, common stack allocations. This is again TSS stuff. It's allocating a stack for it, I think, in the PMM. They've got a predetermined CPU stack size, which I can find. So 10,000, well, that's not 10,000 bytes, that's hexadecimal. Oh. Let's do programmer hex. So it's a 65,536 byte stack. Is what that is. Yeah, the calculator in Windows is a lifesaver for quickly doing decimal to hex lookups, and vice versa. It even lets you do bit shift stuff as well, which is nice. So yeah, it's got a 65k byte stack. Scheduler stack, common int stack, which is interrupt stack, I guess. Common int stack physical. The scheduler stack. Enable PAT, write combining, write protect. Not sure what that is. Page tables. Enables SSE and SSE2. Doing that in the control register 0 and the control register 4. And then sys enter looks like a setting that somebody else sets, probably detecting support for that. Yeah, so this is where we're going a bit out of depth here. Definitely going out of depth. Don't know what this xsave is. Oh, that's the floating point unit. But yeah, what's xsave? Saving AVX state using xsave. Again, what's AVX? So it looks like we've got some CPU features that are probably turned off on each core that need turning on, is what I'm assuming here. using legacy FX save, so it looks like a fallback operation if you don't have a certain instruction enabled. Yeah, so it's all floating point unit stuff, I think. And then, oh, they're initializing the LAPIC again, which is catching the spurious interrupts and initializing the timer. Using the pit timing. So that's interesting, though, what that's doing, because you're getting the timer frequency per core through there. Yeah, it's doing a measure here. Samples, total ticks, blah, blah, blah. That's eventually what we'll want to do too. That's also on the to-do list, is understanding how to initialize that. The pick timer. Need to add a calculator to the OS. Yeah, that would be cool. You know what I was thinking of, and I'm probably going to do this. Call me crazy, but I think it would be an amazing learning curve, and I'm so down for it. What do you think to creating a custom programming language for the OS? So what that would entail is, just to lay that out, is not only do I need to come up with the language and then create a parser for that language and break it down into tokens and all that kind of stuff. There's going to be the whole concept of optimizing code. Like what GCC is really good at is stripping out code and understanding what dead code paths are, but we won't have any of those fancy features to begin with. It would be very basic of parsing the language and then turning that into assembly instructions, and then baking those assembly instructions into a compiled ELF file. So an ELF, I don't know if you know what that is, but it's like the file format almost. You can think of it as a file, but it's the format of an executable, program. So like your kernel is an ELF, right? And you load that into RAM and it executes the ELF. So we could have a custom language, a compiler written in C, and then we'll compile it down to our own instruction set for our operating system. But the whole concept of having, so I know it's going to be shit, right? And very not optimized, but the amazing learning curve is understanding how programming languages are converted from their raw syntax down into a set of assembly instructions and how you build that ELF file. And that's going to be amazing, right? Because then, it'll open it'll open my eyes at least to seeing what compilers are doing on other platforms more. But I think the more I'm thinking about it, and I know it's going to be a lot of work, but I'm so down for it because it's exciting and it's such a wicked learning curve. So I'll have to eventually fantasize about what the language is going to look like, the kind of features it's going to have. Like I'm very positive about Golang, but it does have some things that irk me. So it's nice how it drops the support of having class syntax, and I'm not sure I like that. Like you can obviously achieve object-oriented programming in Golang without class syntax, but them dropping class syntax makes it a bit more what's what I'm looking for. It's just harder to read and write overall. Like the net positive of dropping that syntax is negative to me. So I'd want something with like the class syntax back in, not so much like crazy error checking that Golang has, but the standard stuff of like variables and functions and oh, and there's another thing about it too. See, this opens up a whole world of craziness. So we might want to make a memory manager so that language doesn't have to deal with memory, just like what Golang gives you, right? Now in C, you have to deal with your own Alex and freeze, right? But we could bake into our language framework a virtual memory manager so that when you're creating objects, it has a garbage collector. And again, it doesn't need to be amazing. We know that there are really clever Google people that work on these things all the time, and they have amazing features, but we'll get to open the box of understanding what a hello world garbage collector looks like and the kind of problems you have to solve for that. So yeah, I mean, just talking about it for as long as I have been right now just shows you how insanely complex that can fan out to be. And it would certainly make for an interesting project, wouldn't it? Lily language, yeah. It's almost like the mascot of this OS is becoming Lily the plant. Blorlang. Sounds a bit too much to say. Like C and C++ were obvious, but where does Blorlang come from? It's inspired from Golang, so I guess it makes sense to call it Blorlang. Maybe. From BlorOS and Golang, yeah. So yeah, we'll definitely put that on the roadmap. I'll have a bit of a think later about what we're going to do. And how that fits, and I'll have to do some research offline about it. But yeah, so something in between Golang and C#, maybe. And then, yeah, that would be amazing for us. Like we can wrap that all up into like understanding how we do programs and threading and scheduling of processes and the whole TSS. I don't understand the point of this interrupt toggle. You're telling it, okay, state true. It gets the current state and then turns the interrupts on. So the only thing it's good for is returning what the state of the current interrupt thingy was. So does it use that in other use cases to know if the interrupts are already turned off? And then make sure not to re-toggle them on, maybe. That's probably what it's doing. So like nested interrupt toggling. So yeah, and then once these CPUs are online, So again, looking at this other OS's code, it sends it off to the scheduler. And for some godforsaken reason here, there's a delay of, is that milliseconds? Oh no, it's even smaller. What's US in seconds? Go Blore. So I'm not sure why that delay is introduced. That's a bit random. And then it halts the processor. I'm assuming, so it puts the core back into a sleeping state, but you've initialized some interrupts. And there's probably an interrupt on those cores that are going to wake it up to do some work. Blore Go plus plus. Keep the names flowing. Keep them flowing. And then maybe one will stick out to me and I'll be like, oh yeah, I love that. Da, 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 da. So there's a whole world in this wonderful Lyra OS of things we're not yet clued up on. And that's the basics of scheduling, the task state scheduler, the TSS stuff, and general CPU initialization, so like the FPU. Like everything that's happening in here is setting up GDT, IDT, TSS. Don't know what this VMM switched to. There's still a bit of a question mark over this. Control register 3. Don't know what that is. So we need to look up control register 3. There's the FPU stroke SSE, I think it is. Yeah, SSE and SSE2. And then there's also PTT, which I think is the paging table. So it's the PAT. Paging, actually, if we look, it's writing on that address. I'm just going to make note of that. Look what that is doing. Lily C#. What about Lily C? Or C Lily? I like the word, I like the sound of C Lily. It sounds fun to say, you know? Yeah. I'm wondering if you have to do like with a hyphen in between. We're not doing basic. Are you guys pro semicolons or no semicolons? I need to make a Twitter poll for this. Answers may or may not be influencing All right, let's do da 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 da. Semicolon, no semicolon. Whoops. Where's my keyboard stop working? That was weird. My keyboard is being weird. It's not typing. What is this magic? It must be Twitter going stupid. Da, 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 da. All right, the poll is up. Last time I did a poll, I got 50 responses, so we should get a pretty good sample size. I've got a feeling that people prefer semicolons. Blur basic, basic blur. God. We cannot have the word basic. All right, let me cherry pick some more stuff out of here. So we got the FPU in there, didn't we? FPU, SSE, SCE2, the PAT. We need to read up on CR3. And then scheduling. So a really, really hello world basic scheduler is what we need. It's already over. I should put a link to my BlurOS, shouldn't I, somewhere in my Twitter profile one day. That would be good. All right, so other than that then, there's not a lot to CPU initializing. It's not that bad, apart from, oh, we need VMM. Oh, that's what the CR3 is, right? And then that's it really. So there's not much else we can gather from there. So we're going to go off and look at what the TSS is. And I've not, I don't know anything about the TSS. So we're going to have a little read up on what this guy is all about and why it exists. Task state segments. So the system architecture overview. Hardware task switches are not supported in 64-bit mode. However, the TSSs continue to exist. The base address of a TSS is specified by its descriptor. A stack pointer address for each privilege level. Pointer addresses for interrupt stack table. Okay. The I/O permission bitmap from the TSS base. Doesn't mean much to me at the moment. Now, I do think there's a whole chapter on this somewhere. I think it's this, yeah, task state segment. So it's not got a lot of pages. Doesn't look crazy. Let's go see what this thing's about then. A task is a unit of work that a processor can dispatch, execute, and suspend. It can be used to execute a program, a task or process, an operating system service utility, an interrupt or an exception handler, or a kernel or executive utility. The IA32 architecture provides a mechanism for saving the state of a task for dispatching tasks for execution and switching from one task to another. When operating in protected mode, all processor execution takes place within a task. Even simple systems must define at least one task. More complex systems can use the processor's task management facilities to support multitasking applications. Now, I'm just going to skip ahead and see what it has to say about 64-bit mode, because I've got a feeling this might be legacy stuff. Okay, here we are. Let's just read this bit. In 64-bit mode, task switching is not supported, but the TSS descriptors still exist. The format of a 64-bit TSS is described in section 8.7. In 64-bit mode, the TSS descriptor is expanded to 16 bytes. This expansion also applies to an LDT descriptor in 64-bit mode. Table 3.2 provides the encoding information for the segment type field. So, let's look at figure 8.4. Base address, type, busy flag, available for use, privilege, granularity, limit, present, type. The task register holds a 16-bit segment selector and the entire segment descriptor, which is 32-bit base address, 64 bits in 64-bit mode, 16-bit segment limit and descriptor attributes for the TSS of the current task. The information is copied from the TSS descriptor in the GDT for the current task. This information is copied from the descriptor in the GDT for the current task. Alright. Figure 8.5 shows the path the processor uses to access the TSS using the information in the task register. So you put the TSS descriptor in the GDT, task register, visible part selector, the descriptor TSS. Right, a test register has a visible part that can be read and changed by the software, and an invisible part maintained by the processor and is invisible by the software. The segment selector in the visible portion points to a TSS descriptor in the GDT. Let's just go and inspect. If Lyra puts the TSS, okay, it does, right. So there's a TSS segment in the GDT. Which, looking by the settings that are set here, since all the address stuff is zeroed, it doesn't care about the address location, it just wants the privilege levels. Maybe, or the flags. The privilege is probably somewhere else, but yeah, so it looks like it just wants it for the flags. Why is that in a different location though? GDT load TSS. Yeah, we're not doing any of this. But that's the bit we're learning right now. The process uses invisible part. Yeah, we've read this. Caching these values in the register makes execution of the task more efficient. The LTR, load task register, and STR, store task register instructions, load and read the visible portion of the task register, which is what we just saw in Lyra in the GDT. Here, LTR. Okay. LTR is a privilege instruction that may be executed only when the CPL is 0. CPL, is that the privilege level? I'm guessing it is. It feels to me like that means core privilege level. Maybe. It's used during system initialization to initial value in the task register. Afterwards, the content of the task register are changed implicitly when a task switch occurs. So I'm hoping it tells me how you do a task switch, and then I can go find out what Lyra is doing with that. The STR stores the visible portion of the task in general purpose registers or memory. This instruction can be executed by code running at any privilege level in order to identify the currently running task. However, it is normally used only by operating system software. On power up or reset the processor, segment selector and base address are set to the default of 0. The limit is set to the max. Okay. When a program or procedure makes a call or a jump to a task through a task gate, the CPL on the RPL field of the gate selector pointing to the task gate must be less than or equal to the DPL of the task gate descriptor. Note that when a task gate is used, the DPL of the destination TSS descriptor is not used. Need to provide selective access to tasks. Task gates fill this need. They can reside in an LDT and have a DPL that is different from the TSS descriptor's DPL. Program procedure that does not have sufficient privilege to access the descriptor for a task in the GDT, which usually has a DPL of 0, may be allowed access to the task from a task gate with a higher DPL. Task gates give the operating system greater latitude for limiting access to specific tasks. task gates may also reside in the ID tier, which allow interrupts and exceptions to be handled by handler tasks. When an interrupt or exception vector points to a task gate, the processor switches to the specified task. The processor transfers execution to another task in one of four cases. The current program, the task, or the procedure executes a jump or a call instruction to a descriptor in the GDT. The current program, task, or procedure executes a jump or call instruction to a task state descriptor in the GDT or the current LDT. An interrupt or exception vector points to a task state descriptor. The current task executes an IRET when the NT flag in the eFlags register is set. So jump, call, and IRET instructions, as well as interrupts and exceptions, are all mechanisms for redirecting a program. The referencing of a TSS descriptor or a task gate when calling or jumping to a task or the state of the NT flag determines whether a task switch occurs. I'm losing logic here. The task switching mechanism available in protected mode is not supported in 64-bit mode. So what is it for? Task management and switching must be performed by software. The processor issues a general protection exception if the following is attempted in 64-bit mode. Control transfer to a task state segment or a task gate using jump, call, ints, or an interrupt, or an IRET. Although hardware task switching is not supported in 64-bit mode, a 64-bit task state segment must exist. Okay. Which is why Lyra is probably setting it up here. Is that structure? Can I find where that structure is defined? That is 128 bits. But that's a descriptor. I want sometimes you just gotta go all out yourself. There we are. Ooh. Okay. One more thing I'm going to check. Do we have anything on the OS dev wiki for this? It might be task. verifying me as a human. Okay, let's read this version because it might be a bit more easy to digest. In protected mode, the TSS is primarily suited for hardware task switching, where each individual task has its own TSS. Used in software multitasking, 1 or 2 are also generally used as they allow for entering ring 0 code after an interrupt. In long mode, the TSS has a separate structure and is used to change the stack pointer after an interrupt or permission level change. And you'll have to update the TSS yourself in the multitasking function, as it apparently does not save registers automatically. So we'll skip down to long mode. The TSS does not store information on a task execution state. Instead, it's used to store the interrupt stack table, which is what these are. ISTs. What are these stack pointers? Used to load the stack when a privilege level change occurs from a lower privilege level to a higher one. The stack pointers used to load the stack when an entry in the IDT has an IST value other than 0. And the IOPB, where's that? Oh. Contains a 16-bit offset from the base of the TSS to the IO permission bitmap. Alright. Here we are. For each CPU which executes processes, possibly wanting to do system calls via interrupts, 1 TSS is required. The only interesting fields are SS0 and ESP0. Whenever a system call occurs, the CPU gets the SS0 and the ESP0 value in its TSS and assigns the stack pointer to it. So one or more kernel stacks need to be set up for processes doing system calls. Be aware that a thread's process time slice may end during a system call, passing control to another thread process which may as well perform a system call, ending up in the same stack. Solutions are to create a private kernel stack for each thread process. That marries up to what Lyra does. When we saw, where did we see it? It's on one of their structures. It might be one of the CPU ones. CPU context, maybe? I sneeze. Excuse me. So, wasn't CPU local, that was, or was it the thread? Kernel stack. Process, threads, children, child events. page map PIDs. Okay. Kernel multitasking. Kernel stack per task. Kernel stack per CPU. Setting up a TSS straightforward. An entry in the GDT is needed. Also specifying the TSS address as base. TSS's size as limit. As accessed by flags, TSS members must be set. Gets the kernel data segment descriptor. Oh. Do we even have a kernel data segment? I don't think we do. Let me check. I don't think we do. What's in our GDT? We have a code and data segment. What does Lyra have in its GDT? User data, user code, kernel. Why does it have different sizes? 16, 32, and 64. And it also has the TSS though. Okay. The actual loading of the TSS must take place in protected mode and after the GDT has been loaded. Which is as simple as that. Okay. You are a purple chili to me, Chili. Do you see a different color? Green, okay. So it looks like there's a whole nest of knowledge that I need to take on here. Yeah, I'm going to have to do a lot of reading here. Because what we've got a mix of is I've got a blend of the whole TSS being involved in privileges and jumping in and out or upgrading or downgrading from privileges. And the whole concept of user space and syscalling. And they're all a bit grey area to me. An unpredictable chili. Oh, this line puts it, there are a lot of subtle aspects of user mode and task switching. ESP0 is loaded into the task stack pointer and all system information is pushed before the interrupt handler is entered. Yeah, it's getting into a lot of scary stuff, dudes. So the interrupt stack pointers, the RSP, 16-bit offset to a bitmap for the 64-bit TSS base. To load the TR register with a pointer to the 64-bit TSS responsible for both 64-bit mode programs and compatibility mode programs. That might be why Lyra has 16-bit and 32-bit GDTs. And we can ask the question in the Discord if that's true or not. So that's the end of the TSS section actually in the manual. Holy moly. Look at all these errors that can happen. So we skipped all this bit before. Oh yeah, so this is the process of actually performing a task switch. And that's the code in the processor that's occurring. I just want to read up on the memory. The address space for a task consists of the segments that the task can access. These segments include the code data stack and system segments referenced in the TSS and any other segments accessed by the task code. The segments are mapped into the processor's linear address space, which is in turn mapped into the processor's physical address space, either directly or through paging. The LDT segment field in the TSS can be used to give each task its own LDT. Giving a task its own LDT allows a task address space to be isolated from other tasks by placing the segment descriptors for all the segments associated with the task in the task's LDT. It's also possible for several tasks to use the same LDT. This is a memory-efficient way to allow specific tasks to communicate with or control each other without dropping the protection barriers for the entire system. And because all tasks have access to the GDT, it's also possible to create shared segments accessed through segment descriptors in this table. And if paging is enabled in the control register 3, in the TSS allows each task to have its own set of page tables for mapping linear addresses to physical. Or several tasks can share the same set of page tables. Okay. Damn, it's a lot of configuration. When paging is not enabled, this is the only choice. One linear to physical address space mapping is shared amongst all tasks. Okay. This form of mapping is accomplished by using a different page directory for each task because of the PDBR. Control register 3 is loaded on task switches. Each task may have a different page directory. This mapping is required so that the mapping TSS does not change while the process of reading and updating the TSS is during a task switch. So I need to remember this interesting concept, even though it's really, really hazy to me right now. But the fact that tasks can share the same data You hear some sound when I talk? What sound, dude? It is going through a noise filter, so I wonder if you can hear my fans. Like when I talk, it opens the noise gate, so you're probably hearing other things. Some feedback. Let me just check OBS. That's weird. It's constantly picking something up. I wonder what that could be. If I disable the noise filter, let me know what you can hear. So I've turned off the AI filter thing. Can you hear anything? Yeah, I'm wondering if it's picking up the fans. weird though. It's like a pulse. I wonder if I maybe disconnect my mic. How about now? It's good. That's weird. Because I still see it picking something up on the mic. But if you guys are saying it's okay now, then yeah, we're good. This method of sharing is even more selective than those listed above because other segment scripts from the IDs may point to independent linear addresses which are not shared. Okay. What honestly scares me about this whole thing is that it sounds very elaborate in terms of what you have to set up and how you're going to verify it working. So you've got to be able to, I've got to modify my GDT, I've got to set up the TSS, and then I've got to perform, somehow I've got to perform a task switch and then see and validate things happening inside the task switches. Like that's a lot of ceremony, you know? A lot of stuff. It sounds like probably one of the hardest parts of the OS I'm going to implement by now. We do need to read up on syscalls though. Oh, this is interesting. This is Libra's syscall table. Interesting. And that's the syscall setup. Doing the call from the table here. I wonder what that quad means. Is there an implementation of this? Push. It's kind of like an interrupts handler. Kind of similar. Interesting. It's jumping to the ISR. Huh. Interrupt events handler. Is that what I think it is? Is that an interrupt that's set up? (32) ISR event trigger. And then schedules that. Right, we're going. This is rabbit hole after rabbit hole after rabbit hole. I need to do like a stack trace and go back up the stack where we were at thinking. So we were just interested in understanding what it means to initialize a CPU core. Which is all of this at some point. I wonder if it's worth like we can diverge from having to do this, and we could carry on doing, for example, like a file system driver or even a net driver. Right? We could try and initialize the network card. We could try and go look for the hard disk and interact with the hard disk. And then I can like research into these topics off stream and then do some implementation on stream once I know what we're dealing with. Yeah, I need to have a talk with somebody about how all of these concepts fit together, these Lego bricks. It's getting a bit complicated. One thing we could do, like right now, is so it's funny, we wake the CPU cores up right now, and all we do is tell them to go back to sleep because we don't have a scheduler. What I'm going to do is get the cursor blinking at least. but it's going to be kind of hacky because I'm going to be relying on the HPT timer, which shouldn't be used for this. Like I should be using the LAPIC timers, or the PIT, should I say, which is another piece of code we need to do. Like now we've got this timer set up. We need to use this guy and initialize the PIT timers on the core. Is what we need. And then use those for timing, not this one. But I want to see the cursor flashing, you know? I do want to see that. Now, if we did that through an interrupt handler, it's a bit of a scary concept because you would have to make sure that you're not currently typing on the keyboard, which could be pushing the cursor across the screen, and even in the middle of clearing the old cursor position to render it in its new cursor position, just as the interrupt fires to say blink the cursor. So it could be in a really volatile state. And of course, a way to stop that from happening is spin locking the process, but that sounds expensive. Let's see. Terminal. We'll kind of get it in for now, and then we'll see if it needs to be optimized. I don't feel it does, actually. I can probably get away with spin locking the cursor. We don't have atomic in here, but we do now. Yeah, so we can spin lock when we mutate the cursor position only. Isn't going to be that common, actually. You're going to be really unlucky to get an interrupt firing at the same point that we've just modified that cursor position. And it's going to be such a tiny window of operations. So it's not going to hurt using a spin lock there. We'd have to disable interrupts, so. All right, let's just try and do it. The terminal event is at the bottom. Terminal initialized, T_F, move to next line. Render cursor, clear the cursor. Let's put it here. Da, 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 da. So to toggle, we're going to need cursor visible state. Now, yeah, we're going to just have to lock it. Cursor. So we'll invert its visibility, and then we'll render cursor, renders the input cursor, glyph height, draws a line, input render x, y, term color, clear cursor. If we're not true, then we don't render. So we'll clear the cursor and we'll render it. With it flipped. And then the timer itself, which is set up inside of HPET, and again, this is all a bit hacky, but it is a tiny hack. It's just to get the cursor working. So we'll half the comparator value. And that should get us a blinking cursor. And there it is. Can you see it blinking? That easy. But like I say, it's using the wrong timer. It shouldn't be using the high performance timer. So yeah, it's correctly blinking even as I type. Which is cool. I mean, it feels way better just having it hacky like this, you know. You're glued. Is it that exciting, Fly? Hello, world. It's so exciting that we got it that far, but it seems like nothing now. Like, I can tell we can get user space programs like proper using the cores to schedule programs. and then understand what this syscall stuff's doing. And then we can start thinking about C-Lily. Is that what we decided on, by the way? Is that what we're going with? You guys like C-Lily? All right, it's official. It's official, guys. BlurOS will have its own programming language called C-Lily. And it's going to be a hybrid between Golang and C#. It might be, funny enough, it might just be exactly what Golang is, but with the added class syntax. But oh my god, isn't it going to be so effing cool? Like, can you imagine me writing C-Lily script? Like, you actually see a code file called .cl, and then I run that through a compiler, and it creates an executable binary that we ask the OS to execute. Wouldn't that be absolutely mind-blowing? Like, I absolutely love the idea of that. Like, it's so exciting to me. People will be like, oh, you're writing your own OS. You're like, yeah, and I'm writing my programs in my own programming language, dude. Like, it's just beyond coolness, right? It's like C's not good enough for you. You need your own programming language. Yeah, okay, so roadmap. Roadmap for the OS is I'm going to look at doing the core, the per core timers, which is the PIT. Now that we've got the HPET, so that needs to be done. So it's boxed off, and it's like, okay, that module is done forever, right? I don't need to worry about timers. We need to understand syscalls. We need to understand the TSS and the GDT, IDT setup for that. And the memory mapping. So that's a huge learning curve. And then we'll look at user mode or user space. And then we'll begin C-Lily. And then after C-Lily exists, we're going to do networking. And then we're going to do file systems. Oh, and somewhere between all of this, we need a, let me just put this in here, 3A. Need a basic scheduler. So that's our roadmap. Where's Fly's calculator? That'll come after C-Lily. So the first program that'll appear is going to be calculator. That's going to be a lot for that programming languages to support, because you don't want standard input output, like terminal level input capturing and stuff like that. That's going to be interesting to think about. It's also going to be interesting to think about programs using the kernel terminal. So we might have to duplicate our terminal code and create a terminal in C in user space. Oh boy, it honestly feels like this part of the roadmap is going to be a mountain to climb. This stuff. Um, Initializing the pit timers, not so bad, because that's all over OS dev. Got plenty of resources for doing the pit stuff, which is this guy. No, it's not called the pit. The pit is the programmable interval timer. The APIC timer that I'm thinking about. The local APIC timer. Which is just this here. Perform a pit supported sleep. Now we know how often the APIC timer has ticked in 10 milliseconds. I've got a feeling that's going to be the where we plug in the HPET timer. But that's interrupt driven, so I wonder how we're going to do that. It's going to be weird. Start the timer as a periodic on IRQ0, divider 16 with the number of ticks we counted. Interesting. We could use the HPET to increment a variable. In milliseconds, maybe. I wonder if that's going to be accurate. Okay, cool. So we got the blinking cursor. That was one thing I wanted to do today. And I wanted to wake up the CPUs, but that has opened up a Pandora's box of things that we've got to learn. Just commit all of this. Yeah, even though it's a short 2 hours, it was quite a lot of cool stuff, right? Like what we've opened up a lot of interesting avenues. We've decided on Cellularly, and that's got a place in the roadmap of things to do now. And we've got a whole blob of knowledge that we're going to be absorbing and, getting into user space. That's going to be fun. Yeah, I'm definitely going to keep the name. But yeah, hybrid between C# and Golang. Let's go. We're going to make it happen. 100% we're going to see that thing through, you know? Be awesome. But yeah, I'm going to switch off for the day because honestly, that's just a ton of stuff I need to go bookworm now and have discussions with people about how it works. You know, what does a syscall do? How do you set it up? What's the basic scheduler look like? How does the TSS all fit in? All of that wonderful knowledge. And if I get to a point tomorrow where I can stream, so I might do like the core timers. It might be fun just to get this blob of stuff in there. So yeah. Thanks for stopping by, guys, and I'll probably see you over the weekend, tomorrow or Sunday. All right, my dudes. See you later.